let's get started. My name is Alex Williamson, and in this session we're going to talk about VFIO device assignment quirks and how to use them, how to make devices work better with them, really, for troublesome devices. I'm sure everybody's heard about VFIO by now, today, maybe yesterday, but let's do a really quick refresher. Our time is limited, so I'll keep it short. But VFIO is basically a user space driver interface. We decompose devices into a user space API. The core of that API is an IOMMU group, where a group is the smallest set of devices that are DMA isolated from all other groups. Isolation of that group is an important part of some of the quirks we'll talk about. And the VFIO container, the user creates a VFIO container, adds the group to that container, and that represents the IOMMU context for one or more groups. That allows them the ability to get access to a VFIO device. The VFIO device is segmented into regions, where the regions represent things like PCI config space, if it's a PCI device, MMIO spaces, IO port spaces. We have device-specific spaces as well. We have a number of I/O controls for interacting with the containers and groups and devices, and we usually configure interrupts via event FDs via those I/O controls. So being a user space driver interface, we need user space drivers, where when we're talking about a VM, we're really talking about QEMU is the user space driver, and that recomposes the device back into a new virtual device. And the virtualness of that device is something we'll talk about here today too. So the overall end-to-end view of VFIO is that we have a kernel driver that exposes a user interface that is consumed by a user space driver, and in the VM case, becomes a new virtual device in the VM. And has been kindly referenced a few times. Please take a look at my KVM Forum talk from 2 years ago. There's a video on the KVM Forum channel page that goes into this in much more detail than I can provide in 2 minutes. So here we're going to be talking about quirks. And so let's start out with, what is a quirk? I'm not sure how universal this term is, but in the kernel we like to call quirks any piece of software that fixes the device and makes it work more how we want to. And in the case of VFIO, we're talking about missing and broken features and topology changes and additional virtualization for the most part. And where can we make use of those quirks? I guess I missed that slide. Didn't show up in this one. We can pretty much make use of quirks anywhere in the VFIO stack. But something we need to be concerned with when we're implementing quirks is the performance effect we have on the device. So when we're modifying things in config space, that's pretty much free because config space is usually considered to be a slow path anyway. But when we start interacting with MMIO spaces, we need to be sure that that's not a performance path. Some of the interrupt types we'll deal with, we have to virtualize parts of the MMIO space of the device, and we have to be careful about how that affects access to other registers, because that implies that we're trapping into QEMU rather than providing direct access to those. So in our model of VFIO to user space, we have isolation quirks. So I mentioned the IOMMU groups. Isolation quirks are targeting how we consider the isolation of individual devices, the size of those groups, because we want the groups to be as small as possible so we have the greatest granularity in our ability to use them in different ways with user space. Aliasing is also another issue related to the IOMMU of how does the IOMMU see the device? Does it use the correct requester ID? We've seen talks referring to the BDF, the bus device function number of devices. That's the requester ID and how the IOMMU selects the set of context tables that is used for that device. So we have quirks correcting issues with that. Resets, how does the device get back to an initial state? How do we wipe the state from the device? There are ways to do this, but they often don't work. Sometimes they're not implemented. Sometimes we need device-specific things. And sometimes we'll implement those quirks in QEMU. So whenever we're implementing quirks, there's a question of, is this applicable to the kernel? Is it specific to the virtual machine? Is it robust? So we might implement Quirks in QEMU simply because they're not good enough for the kernel. Virtualization, every device needs some degree of virtualization. Some devices need more, so oftentimes if it's VM specific, we'll implement that in QEMU, but we can also implement it in the kernel. And again, it's another question of, is this generally useful? Things like PCI bars, we never want the user to have direct access to, so we actually virtualize those both in the kernel and QEMU. We really only make use of one of those virtualization depending on if we're using QEMU or something like DBDK. But that's a case where it makes sense to do it in the kernel as well. So I thought maybe the best way to look at what we can do is to look at what we have done. But let me start out with a disclaimer. It's always fun to pick on hardware that's broken, but that's not really the goal here. Mistakes happen. Things like isolation are only considered when you are targeting device assignment use cases, perhaps. So we've worked with a number of hardware vendors to correct mistakes. Some of those vendors have gone on to implement them in hardware, so I think we should always encourage making devices work better with device assignment. So stepping back through each one of our little Quirk band-aids, we can start with isolation, and as I mentioned, this is targeting how our devices segmented into IMEI groups. In PCI devices, we're really looking at access control services and our ability to enforce whether transactions are always targeted upstream towards the IMEU or whether untranslated requests can take peer-to-peer routes through lower leafs of the topology. So whenever we don't have ACS, we assume that redirection is possible. Not having ACS doesn't necessarily mean that peer-to-peer happens, but without ACS, we have no indication that it doesn't. So whenever there's not ACS, that increases the size of our IMEI groups, decreases the granularity with which we can do assignment, and it's generally a bad thing. So I always encourage vendors to implement ACS, but when they don't have ACS, we can work with them to determine whether the devices and the interconnects implement equivalent routing, and we can implement Quirks for those. So some examples, and let me start out at the root ports, because when you're dealing with ACS grouping, it is the isolation of the device from the endpoint all the way to the IMEU. So the top level of the PCI Express topology is the most important for having isolation, because if we don't have isolation there, we can't have isolation anywhere downstream. And of course, a lot of chipsets came out before we started really looking at device assignment and what are the requirements of doing device assignment. So there are a number of Intel chipsets listed here where the Southbridge, the PCH root ports, do not implement ACS, but the chipset itself has features that allow us to implement equivalent ACS. So we've worked with Intel to provide that. And we got a little step further in the next generation of chipsets. They actually did implement ACS, but the register size was wrong. So we actually had to implement a different implementation of ACS to work around these. So that was also implemented as a quirk. And finally, in the latest chipsets, it seems like we have ACS and it's working well. So that's an example of where we have worked with the vendors and they have incrementally improved the hardware to make it better for device assignment. On the client processor side, unfortunately, we still don't have ACS and we don't have isolation guarantees and we don't have quirks, and that's often an issue for people. And unfortunately, the recommendation there is to use server processors. Most of the hardware vendors are really targeting device assignment as a server feature. And even though we can do it on our laptops today, it's not always the easiest thing to do. So some more examples, AMD Ryzen processors, when they came out, were also lacking ACS. Luckily, this was something that was in the hardware but not exposed. So firmware updates were able to fix that. We don't actually need quirks for those. Endpoint devices are constantly having ACS issues. Anytime we have multifunction endpoints, we need ACS to separate those functions into separate groups. So there are numerous chipset examples. The ARM vendors are not immune from these issues. Intel NICs is another example where we had many devices released before we really understood that we need this sort of isolation. We have a ton of Quirks to handle the multifunction NICs, and the newer NICs now do implement ACS. And NICs from other vendors as well also implement Quirks for some of these things. So the overall story with isolation is, it was bad, but we're getting better. And it's increasingly common. And if there are hardware vendors in the room, please implement ACS on all downstream ports and multifunction endpoints. There is some ongoing discussion about upstream ports on switches, but when usually switches are making use of single function upstream ports, and we believe we have the correct algorithm for ignoring those for now. DMA aliasing. So does the device actually expose the requester ID, the BDF, that it intends to? We have, this is often a multifunction issue where the device will, regardless of which function you're dealing with, perhaps it only exposes itself to the IMMU through one function. This quirk is actually really both a bare metal and a device assignment issue, because some of these devices were developed years ago when IMMUs were not very common. And now that they are common, you see the problems even on laptops just trying to turn on the IMMU on the host system. So some examples, the multifunction devices, the first two examples are cases where it's a multifunction device and the hardware simply uses the wrong requester ID. And so we have to alias those two, any devices that use that requester ID with the device that actually matches the BDF that the IMMU sees. So that expands the IMMU group, because obviously if the IMMU can't distinguish between devices, we can't separate them. There's an example of an Adaptec device where it makes use of a bridge, and actually not only is the function wrong, the slot number is wrong. And then we also have non-transparent bridges. And this is probably the one that is continuing to be an ongoing problem. Typically, when you have a PCI bridge, you can discover the devices downstream and you can enumerate those devices. When you have a non-transparent bridge, you cannot see the devices on the other side. So these non-transparent bridges are often used for connecting two nodes of a system together, and you have proprietary drivers that communicate across those bridges. So the host system can't actually see what it is that's generating the DMA. And so far, we've been using Quirks to fill in those gaps, to let the IMMU know what to expect is coming across that bridge. So the advice here for avoiding Quirks is, of course, that hardware designs must consider the IMMUs and use predictable and discoverable requester IDs. We may still have an ongoing problem with transparent bridges until we have some sort of architectural specification of how to handle those, though. Resets, so we want to return devices to known states. We want to wipe the device between use cases. And PCI provides a number of mechanisms to do this. There are various function level resets, there are power management resets, there are bus resets and slot resets. The slot and bus resets have some scoping issues that you're affecting multiple devices when you do that reset. So that makes them a little bit less ideal for device assignment use cases. Often that's okay when we have things like graphics cards assignment and your bus consists of a GPU and an audio function, because those are usually assigned together anyway. But in an ideal scale-out system, you want FLR available, but it's apparently still difficult to implement sometimes. Some examples here. We have some NVMe devices, and NVMe is interesting because the specification actually requires the device to implement FLR, but it doesn't always work. So there are some older Intel NVMe devices that if we talk to them too quickly after an FLR, they lock up and no longer work, so we have to add an extra delay. There are Samsung devices that actually drop off the PCI bus when we reset them, if they're in the right condition, and we found that if we disable the NVMe controller before we do that reset, then they behave correctly. So we have a quirk in the host kernel that stops the NVMe controller, then does the FLR, and they seem to be more stable that way. Radeon graphics are kind of a persistent problem. We have some quirks, and sometimes these devices work great, sometimes they don't. This is probably one where we would really appreciate some more input from AMD on how we can make nice isolated reset quirks to make those devices work better. Wireless cards, kind of similar problems to the Samsung NVMe controller, except we don't know how to fix them. So they drop off the bus when we do a bus reset, and our only quirk there is to not do a bus reset. So just avoid the problem, which means that we're not wiping the device, we're not getting that clean state, but at least the host system works. Threadripper, AMD's workstation processor, initially had some issues doing bus resets, and it wouldn't enumerate anything downstream of the bus after it was reset. There were some patches proposed, but luckily this one was also fixed in firmware, so avoided another quirk there. But we do have this ability to implement device-specific resets to modify how resets work. So if a device doesn't expose a reset but can be reset, we can make it work with quirks. Virtualization is really the asterisk in the device and the new device in QEMU. So all devices need some degree of virtualization. As I mentioned before, the PCI bars we have to virtualize because we're transposing the device into a different address space. The MMU only handles the translation of the DMA, not the MMIO and IO port spaces of the device. Sometimes we're moving the device in the topology. Root complex devices become endpoints under root ports. Multifunction devices become single function devices. All those sorts of things are just a normal part of the virtualization of the device. But some things require a little extra. VGA is a prime example of this one. And I've given previous talks on this. The latter one, you can find the video on the KVM forum talk. I believe the first one was before we started recording, but I would encourage going to look at those. The general problem there is that these devices step through different address spaces from VGA space to IO port space to MMIO space, and they can actually access PCI configuration space through numerous ones of those. So they're getting the physical addresses rather than the guest physical addresses. And the IMUI protects us from them doing anything bad, but the drivers don't work unless we provide the virtualization. Intel graphics is a notoriously difficult to virtualize device. The graphics translation table is just one of the issues that it has. The addresses that it uses for stolen memory are effectively latched into the hardware on boot. And so we have to trap the programming of that to relocate it to a VM allocated stolen memory region. So that one is always troublesome, but luckily we have vGPU to avoid those sorts of issues with IGD. The I40 graphics or I40 network adapter, when we're doing assignment of the physical function, in order to virtualize interrupts, legacy interrupts, we need the PCI device to support generically telling us the interrupt status and also providing us a way to mask the interrupt. The I40E only provides the latter one of those. It allows us to mask the interrupt, but we don't know when it's signaling. So if we try to assign this device using legacy interrupts, it just screams on the host and generates a flood of interrupts, and it gets shot down by the host kernel. So in that case, we've virtualized the legacy interrupts to not expose it to the guest and make sure that we're always disabling that interrupt. So effectively, it becomes a physical function without legacy interrupts. On the flip side, there's a new quirk going in for 4.20 where an SROV VF actually reports a pin register indicating that it does support legacy interrupts, but virtual functions are not allowed to support legacy interrupts, and it doesn't, so we need to virtualize that pin to mask that problem. We have a couple MSIX issues. We have a Realtek card that exposes MSI through a backdoor in its MMIO space. So that's another case where it's exposing physical addresses to the device, allows the user to program those, and we have to virtualize that. And I'll skip Chelsea.io because we're running out of time, but I will mention that we do have MSIX relocation. So that problem I mentioned with when we have virtualizing MMIO space, and that can cause performance problems, and we necessarily need to virtualize the MSIX location, we can actually move that. So the PCI spec recommends things like 4 and 8K page sizes, which are just simply not good for things like ARM, where we might be using 64K page sizes. So quickly wrapping up here, I hope this has given you a good idea of things we have quirked, things we can quirk, some of the issues that we need to think about when we're quirking devices. And in general, quote unquote, well-behaved devices shouldn't need these quirks, but we do have them available to us when we need to make devices that are troublesome work well. And again, for hardware designers, things to do to avoid these sorts of quirks. ACS, as I mentioned, provides us the isolation we need, gets those IMEI group sizes smaller. Working function level resets, shouldn't need to say working and provide this feature, but we do. And avoid leaking any sorts of physical addresses. So we should only be looking at physical addresses of the device through the PCI config space. Anytime you can get to those through MMIO space, and the driver makes use of those, are potentially cases where we need to virtualize. And as I mentioned with the MSIX bar, it seems like the best way to avoid page size issues with MSIX vector table is to simply make use of the MSIX table in a different bar, a separate bar from anything else. And then you don't have to worry about those sorts of issues. So I don't know if I have any time for questions, but if there are any.
Hi, Alex. I have 2 questions. One is about FLRAF. Can you explain what's that?
So there are 2 different implementations of FLR. One can be implemented through an advanced function capability, which was, I believe it was specified so that you could implement it with a PCI, conventional PCI device, because it doesn't require the PCIe capability. And then the other one is through the PCIe capability itself. So it's just 2 different mechanisms in PCI config space to trigger an FLR.
Okay. So the other one is about the AMD Radeon, about the bus reset. Mm-hmm. The problem you encounter is seeing that the reset cannot come back, or the reset method is not supported. So
in most graphics cards, there is no FLR support. Perhaps the ones you're working on, there are, hopefully. So we generally do a bus reset, and then the device doesn't come back. So
the bus reset, you are referring to hotlane reset or secondary bus reset?
Secondary bus reset. Okay. Yeah, so the device doesn't come back. We understood that there were some actual ASIC issues on the Bonaire and Hawaii chips. And we do have, those are the quirks that we've implemented in QEMU that are kind of 80% stable. Mm-hmm. But we see users randomly complaining about other devices, and it seems like some users have great success and other users don't. So I don't know if they're using different chips or, but if we could have you as a contact for working on those, that'd be great.
Yeah, I think you can contact me for that reset. We have some tricks that how to make it work, and actually we implement the other mixers of reset proprietary AMD solutions that would make the GPU compare properly. Okay. And in the virtualization cases, actually we have a few other reset mixers that are able to reset the GPU like contiguously reset 1,000 times or maybe up to 2,000 times. It can compare perfectly. No problem.
Yeah, I understand there are some improvements in the AMD GPU driver for reset, and if we could port some of those to the general reset quirks, that would be great for making use of them in device assignment.
Thank you.
Yeah, thanks.
Just real quick, are there any quirks for the reserved region? I mean, device with like RMR reserved region, you can still...
Those are an issue as well. So generally RMRRs are, They're VTD specific, and they specify that the host should have an identity mapping of that RMR range through the IMMU. And we've taken the approach that for USB devices, we think they're only used for emulation of basically PS2 support. And so we generally ignore the RMR for those. For graphics, we believe they're usually used for stolen memory, and we think that we can ignore them too, but they are causing us some serious issues because we're trying to implement code for an IOVA list, so we know what ranges of IOVA space we can actually make use of, and those RMRRs are coming up as reserved regions that we cannot make use of, and so we can't continue, we have a conflicting requirement that we want to know what IMMU ranges we can use and what we can't, and we were using those previously, just ignoring them, and now we have an issue that we can't. So if you have any input on how we can resolve that, it would be great. Okay.
Okay, thank you.
Thanks.